G'day, Quantum Odyssey mates. This is Hadamard Gate, your Quantum Odyssey tour guide. I do have another announcement, although it's slightly belated. Yesterday was Earth Day, so April the 22nd, and it was inaugurated to spread awareness of keeping care of the Earth to prevent the effects of devastating climate change, because right now it seems like our world is warming at an unprecedented rate, and we must not tip the balance. We must not exceed 2 degrees Celsius over the long term average since the 1800s. So, and quantum currently has been shown to have promising applications on modeling climate to tackle the pervasive issue of climate change. As a result, I am joining the Risk Management and Insurance Challenge by the World Bank as part of the Potomac Quantum Industry International Year of Quantum Global Industry Challenge. So I'm actually going to recruit a few more team members, so please don't miss out. You probably have only a few hours for me to form this team, but I'm definitely looking for those with financial and business knowledge and how to mitigate the risks on the insurance sector in light of ever more frequent natural disasters. Remember, we want a green world, a sustainable world, and we want our technologies to be sustainable as well. So we need to be mindful of the Earth's limits and not use up too much of Earth's resources, which especially could cause inequality and future shortages in the long run. We don't want this to happen. We don't want mass extinctions. We don't want a sixth extinction anymore. So this is the topic for Earth Week. Yes, I have to make another special announcement for you, but I'm also announcing that I will be hosting Friday sessions at midnight UTC, so Friday, Saturday at UTC, so 00.00 UTC. Friday, Saturday, Friday, Saturday 0.0 UTC. Hopefully to get some more traction on this 50-day challenge. Let's go to today's topic. Today's topic will be about matrix multiplication. So it's still going to be a slight diversion from Quantum Odyssey, but it will definitely help you in visualizing how the Hadamard Gate works. So this is a general one gate qubit gate, and the Hadamard Gate has only the rightmost straight lane red, while all the other 3 wires of this gate are blue. Notice that when splitting, you split the areas, but when you merge, you add or subtract the radii. This is the subtlety about gates which split and merge sigils. The ringed sigil over there, these, let's call them eyes, represent generic sigils that have both a real and an imaginary component, and they are not equal. These are the most difficult qubits sigils to deal with. The yin-yang are those which point diagonally, so they have both a real and an imaginary component, and they are equal. and the solids only have like a real component or an imaginary component, but not both. We will demonstrate matrix multiplication using on an arbitrary qubit state using this visualization. So what is a Hadamard gate? The Hadamard gate is 1 over root 2. Then here's where it goes. The left lane splits equally between the left and the right, so it's 1, 1. So left, left, input, left input, and then the right lane splits equally to both lanes, but the right wiring is red, so it's -1. So 1 minus 1. Over there. So left input, right input. So left input, right input. Likewise, the output that's receiving from the inputs would be this. Left output, right output. So let's move it over there. And then we apply this to the vector, which has only one element dimension. So 2. So that means it will be expressed as a column because it is row major. So we have alpha plus beta I, gamma plus delta I over there. And everything would be divided by the square root of 2. Okay, the result would be this. The input of the left will be distributed to both of the left, so that will be alpha plus beta I, so it will work as this: alpha plus beta I, alpha plus beta I. So now you distribute these two equally, and everything is to be divided by a factor of 1 over root 2. And then for the right half, the left half would receive of the output will receive a positive copy of gamma plus delta I, but the other half would receive like a negative copy, minus gamma minus delta I over there. We can simplify this expression to 1 over root 2. Then the real component would be alpha plus gamma, then plus beta plus delta I, then we have alpha minus gamma plus beta minus delta I. So once again, left input, right output, right output. This is the input. This 1 over root 2, then the matrix of 1s and negative 1s is H. The vector, the row vector with only one dimension index would be ket psi. So that's how to visualize a Hadamard in matrix multiplication. On the left, the components are sums of constituent, and then diff of constituent components. We will move on to an important topic that will prove useful in understanding the mathematics behind quantum mechanics. So, and the topic we will discuss about will be an exciting journey, even though it has a reputation of just being as esoteric as quantum mechanics, possibly even more, and it's a fan favorite of both mathematicians and physicists. That's the Lie groups. When you hear about the Lie group, the first image you probably comes up to would be like an 8-dimensional crystal called E8. E8 would be, and then it has like this relation between the mirrors. So a branch, a 3-branched diagram. So there's a triality on the middle. One branch is of length 1, the other is of length 2, and the last one is of length 4. The E series. The E series, what makes it an E series is that the diagram branches into two, but one of the branches has of length 1, and the other one has of length 2. And then the rest of them, let's call this the body. It is said to be the most beautiful and complex mathematical object ever devised, and it has 240 dimensions. So that's probably the impression of what a Lie group or Lie algebra is when you type it on Google. So this is what you even get if you type it on Google. So this object over there is called the E8. But the concept of a Lie algebra is surprisingly simple. It's just a way to mathematically represent a rotation in common space. And then you can generalize this to high-dimensional spaces and complex elements. So here is an example of a Lie group. The simplest examples of the Lie groups are, let's say, the real line with addition as the operator. So the real line with addition as the operator. We then have the complex numbers on the complex star. And then multiplication. Then we have the circle group, which is also called S1. So S1, and then the multiplication, which is just defined as e to the I theta, which theta is a real number. Nothing more than that. We have the two-dimensional rotations, SO2. SO2 is nothing more than cosine theta minus sine theta, sine theta, cosine theta, which theta is a real number. And then a similar idea for three-dimensional transformations and linear transforms, which is just the set of invertible matrices under matrix multiplication. Matrix multiplication is the central operation on Lie groups that are represented as matrices. The set of all legitimate quantum gates itself form a Lie group, namely the special unitary group or the unitary group, like actually just the unitary group of 2 to the n elements. Then why did Lie groups even come into play? Actually, the story of that is it's actually motivated by investigating whether differential equations are solvable in closed form. This is called differential Galois theory. It is known that there is a cubic formula, there is a quartic formula, but there isn't a quintic formula. And when I mean that, I mean like a formula that involves only the basic arithmetic or field operations and extracting nth roots. There is no such formula in the fifth degree or higher. The reason? It has to do with group theory, which is ultimately has to lend in the study of symmetries. This is where Rubik's Cube comes into play. Rubik's Cube. So now Rubik's Cube comes into play. And now you spin them around. And even then, after discovering that one of those groups that's associated with the symmetries of the roots is not solvable, called non-solvable, that's still a technical wording, Galois proved that you cannot express the roots of a general quintic in terms of extracting roots and the field operators. Likewise, for Galois theory for differential equations, which is Lie theory, in the way, this time, this differential Galois group has to be solvable. It is known that SO2 is solvable, but not SO3, so not solvable, as well as SU of 2 and anything higher. Likewise, you can say that this integral of e to the minus x squared dx, which has applications with the bell curve and its cumulative distribution function, is non-elementary because the antiderivative lies in a non-solvable differential Galois group. So I already gave you explicit examples of Lie groups, which are just like these familiar matrices under matrix multiplication, and if you just multiply them, you still get the element in the same set. So you cannot exit the Lie group just by multiplying repeated matrix elements of a Lie group. The last topic for today is about Lie algebras. Lie algebras, which is actually not named by Lie, Lie called it infinitesimal elements on a continuous group, played a powerful role in capturing the structures of all Lie groups by providing an easier to manage linearized element. So let's investigate SO3. SO3 is of this form. So let's call this. I don't even want to give like the three parameters for SO3. So A, B, C, D, E, F, G, H, I, which such that the vector A, B, C, then D, E, F, G, H, I is orthonormal. So that means, let's say, the dot product between a I, then so on, dot a, this thing over j is equal to delta ij. That's just an if statement saying like it is 1 if the I is equal to j and 0 elsewhere. Or it says that A transpose A is equal to A transpose is equal to I. These two definitions are equivalent, which let's call this A. Then it's associated Lie algebra, however, you can explicitly like extract the elements. Little so in Factor so black letter so, little so3 has a much simpler form. It's nothing more than this: 0, 0, 0, then x, y, z, z neg y neg x. So this is little so3. It's just a skew symmetric matrix. And it greatly simplifies a lot of Lie algebra, Lie group operators. And surprisingly enough, there is a shortcut for converting a Lie algebra element into a Lie group element called matrix exponentiation, which the exponentiation operator is defined in terms of Taylor series. So Taylor series. How do you visualize a Lie algebra? So So while a Lie group represents a particular position, a Lie algebra represents the actual object spinning, how it's spinning. So position, so here's like the example of the globe. So position is in SO3. And then rotation, the rotation itself is modeled as in little so, so fracture so, let's say, of 3. And it has a much easier form. And then how to combine them. You can add them and then you can multiply them. So little so3, this thing can also be simplified even further to just x, y, z, with the cross product as the multiplication operation. So here is a footnote for that. So the main note is the topic for Lie algebras and Lie groups. This one is nothing more than just an impression. It's nothing more than just this session just gives you a basic impression on Lie theory. And that is not even the root systems like the line, which is associated with A1 or SO3 or SU2 or even SL2. Then we have this hexagon, which is associated with SU3. Then we have the square over there to be associated with SO5 or B2. Or even the first of the exceptional ones, the special snowflake, G2, which is best described as the automorphisms of the next level of complexness after the quaternions called the octonions. It's just an impression on what really is Lie theory, not the crystals which make up the imagery of Lie theory. Not the crystals. These topics, regarding like Lie groups and Lie algebras, they will be placed on a separate series, although you will likely learn elements of Lie groups, implicitly or explicitly, during the 50-day challenge. You will also learn how to perform matrix multiplication between two matrices, which is the same as composing two quantum gates in series. And then the tensor product of matrices, which is composing two quantum gates in parallel. Peace out, take care of the Earth, and keep on going.